Dear students, since some of you have requested me to send a problem on Pincer search, I have been recording a video that is a solved example on Pincer search, and this PPT, this video also has the algorithm which is required to solve the problem. Yeah, so in the first two slides, I have put up the algorithm required to solve the Pincer search problem. So the algorithm is something like this. Yeah, so I will be referring to the algorithm every now and then as we go ahead with the problem. So coming to the data set of the problem, this is the data set I have put it here, which has got 5 transactions and the minimum support is 2. I have put a small piece of algorithm which is required to solve the problem till here. This is not the entire algorithm. The entire algorithm is present in the first two slides. So this is the piece of algorithm which is required to solve the steps till here. So as you can see, initially in the step 1, we initialize frequent item set L equals L naught equals null set, K equals 1, and candidate item set C1. It contains all the one item sets, all the candidate one item sets. So if you try to remember the concept behind this algorithm, we have various data structures to be maintained, and this algorithm runs from top down as well as from the bottom up approach. From the top down, to hold the item sets, we have data structures such as MFS and MFCS. MFS full form is maximal frequent set and MFCS full form is maximal frequent candidate set. Maximal frequent set, that is MFS, is used to hold the maximal sets which are frequent, and MFCS, maximal frequent candidate set, is used to hold the items which are candidate and which are maximal in nature. And from the bottom, we have two item sets, that two data structures. Those are L and S. L is to maintain the frequent item sets and S is to maintain infrequent item sets. So initially all the data structures are initialized, and as you can see here, MFCS should contain all the items in the entire transactional database. So MFCS will hold A, B, C, D, E, F, G, H. So it will hold the maximal set, maximal candidate set. And we initialize MFS, that is maximal frequent set, as a null set because we have just started and we do not have any frequent item set which is maximal in nature as of now. So initially we initialize all these data structures. Next, do until ck is equal to 5. So my ck is now c1, k is equal to 1. So c1 is not equal to null set, and that is why I enter the loop, read the database and count the support for CK and MFCS. So I read the database to count for C1 and MFCS, and I get the count something like this, and the count of MFCS is 0 because in no transaction I have all the items together present. So the count of MFCS consists of only one set, and the count of that item set is equal to 0. The next step is MFS equals MFS union frequent item sets in MFCS. Since my minimum support is 2 here, and the frequent item set in MFCS, since the count of MFCS is 0, it is not frequent, and hence MFS equals MFS union. I don't have any item sets frequent in MFCS, so this will be my initially MFS was null, so null union null will be null only. So MFS will be equal to null set. Next, coming to SK, which should contain all the infrequent item sets, and L1, which contains all the frequent items. So SK here is K is 1, so S1 and L1. So S1 contains all uh, um, one item set which are infrequent, and L1 consists of all one item set which are frequent. So this is based on the counts what we have read here. Next, coming to call MFCS generation algorithm. Now this module MFCS generation algorithm is especially called to go on breaking the maximal candidate set that is present, to go on breaking down the maximal candidate set that is present, because we are now following uh, top down approach. We have to go on breaking the maximal candidate set that is present. So the maximal candidate set that what we have is this one, A to H, A B C D E F G H. So we have to break it to find out whether we can get the minimal item sets. So call MFCS generation algorithm since SK is not equal to null. So since S1 is not equal to null, I call MFCS generation. So I have to be doing this with the every item set that is present in S1. So first I take my small letter S as F, and M is nothing but the item set what is there in MFCS. So S is a subset of M. S is a subset of M means F is present in this M. So I should be removing F from M. And when I remove F from M, this M will be changing, and I have to remove this M from MFCS. So MFCS will be initially null set, and then after removing F from this M, I will be getting A, B, C, D, E, G, H. And similarly, next is G. I have to consider the item set G. So I remove G from this MFCS and I get A, B, C, D, E, H. Next, I remove H from MFCS and I get A, B, C, D, E. I get A, B, C, D, E. Yes. So once I'm done with this call MFCS generation algorithm, I have to be doing MFS equals MFS union frequent item sets in MFCS. Now, I am not going to read the count for ABCD once again from the transactional database, because we have not yet read the count for 5 item sets. So as of now, the count of item set that is present in MFCS, that is my initial A, B, C, D, E, F, G, H is 0. My MFS still remains null set only, and MFCS will be A, B, C, D, E only, because MFCS is now A, B, C, D, E minus null set will be the same, A, B, C, D, E. So next, what is the next step? I have to call MFS pruning procedure. Now, what is this MFS pruning procedure? Since this is a bottom up as well as top down approach, what happens is the frequent item sets are maintained in MFS, and frequent item sets are maintained in L also. The item sets which are maintained in MFS, frequent item sets which are maintained in MFS, are maintained there because of the top down approach, and the item sets which are maintained in L are because of the bottom up approach. So what happens is, um, sometimes when we go from top to bottom and bottom to up, it might so happen that some of the item sets which are there in L are also present in MFS. And one more key point of this algorithm is the final answer will be there in MFS. So the point here is that when the frequent item sets are already present in MFS, then why to maintain them in L again? So such, if at all I have any item sets which are present in MFS as well as in L, then I have to remove it from L. So MFS prune procedure is called for that reason, which checks that whether any of the item sets in L are also present in MFS. For all item set C in LK, if C is a subset of any item set in the current MFS, delete C from CK, delete C from LK. So if there are any items which are there in L as well as in MFS, then remove it from L. So now if you see here, my MFS is still null. So when the call happens to this module, if C is a subset of any item set in current MFS, so since current MFS is null here, nothing happens in MFS prune. So there is no action taken in MFS prune. The control just comes out of this module. So even though MFS prune procedure is called, there is no action that takes place. And then the next step is to generate candidate ck plus from ck plus 1 from lk. So we have to generate c2 from l1. So after generating c2 from l1, I get these many sets. And then next step is, if any frequent item set in LK is removed from MFS pruning procedure, call recovery procedure to recover candidates to CK plus 1. So recovery procedure is called only when we remove some item sets in LK. So in my case, what has happened here is that I have no action has been taken place in MFS prune. So no item sets are pruned. So no action once again in recovery. Nothing happens in recovery, or recovery is not called at all. Normally we call recovery whenever we have some item sets in MFS and there are some item sets in L which can be merged and it can be put in CK. For example, I have AB in MFS and I have AC in LK, L2. I can generate ABC in C3. So such an instance may come across. So in that case, we call recovery procedure. Otherwise, such sets like ABC might be left out in case I do not call recovery procedure. So nothing happens in recovery, and next comes the step. Yes, after after recovery procedure, yeah, call Mfcs prune procedure to prune candidates in CK plus 1. Now what it says is that, if why do we call Mfcs procedure? Yes, it's there here, this part. So when do we call MFCS procedure? MFCS procedure is called in order to check whether all items in candidate item set C2 or C3 are also present in a MFCS, because every item that is present in a C must be present in a maximal frequent candidate set. Otherwise there is loss of item sets. There might happen something like some of the items may not get joined with other items in order to get some more items. So every item that is present in C candidate set must also be present in MFCS. So if such items are not there, if C is not a subset of any item in the current MFCS, then you have to delete it from CK. So every item that is present in C should also be present in MFCS. So if you check here, um, AB, so this is my CK C2 and I have to be checking with MFCS. So my current MFCS is ABCDE and this C2 is my current candidate set. So I have to check whether every set here is a subset of this set. So AB, yes, it is a subset here. AC is a subset, AD is a subset, AE is a subset. So every subset here is a subset of the set in the item set in MFCS. So only when all sets here are present here, that means that this is a set which has got maximal sized items. So only then we can assure that all combinations of item sets can be produced. So that is a kind of check that we perform. that every set that is present in C should also be present in MFCS. So yes, so once we do that, what is the next step? So call MFCS prune procedure to prune candidate. So this is something that we have done. So since every item is of C2 is also present in MFCS, nothing gets pruned in MFCS procedure. Next we have to increment K, and then we have to go back in the while loop. So I increment K here, and I go back in the do while loop where I once again read, where I check whether CK is equal to null. My C2 is not equal to null, so I go inside the loop and I read the count for the item sets in the database. Also I read the count for MFCS. So right now the count for all the two item sets are given here, and the count for MFCS, that is A B C D E, the one which we have got from here from the previous step, A B C D E is 1. Now MFCS equals MFCS union frequent item sets in MFCS. So my minimum support is 2, but the support of MFCS what I've got here is 1, and hence it is not frequent. My MFS was initially null, and hence MFS once again remains null. That is MFS equals null union. Null it will be, so MFS is null. Next I have to maintain a set of S2 and L2. So S2 is the infrequent item set. So I see here IAE is the only one with the no support here, minimum support. So S2 will be A2, AE, and L2 will be these many item sets. And I have to call MFCS generation in order to break this MFCS into smaller sets. So since S2 is not equal to null, I call MFCS generation. So call MFCS generation since else S2 is not equal to null. So first consider the single item set. Consider the item set that is present in S2, that is AE, and check whether AE is present in ABCDE. Yes, AE is a subset of ABCDE. So what we have to do? We have to break the MFCS. So first remove A from M. What we get is BCDE. BCDE is not a part of MFCA, so include it. Next you remove E, you get ABCD. So ABC is not a part of current MFCA, so you include it. So after breaking down this, I get two sets, that is BCDE and ABCD. Yeah, so this step is done. Next is this step, that is MFS equals MFS union frequent item sets in MFCS. So yeah, since I have not read the count for 4 item set, I am not going to read the transactional database once again, because the reading of transactional database happens only in the beginning of the do while loop. I do not read it here once again because it is going to be an extra expenditure for us. In case any item set is read over here and we already have the count, then in that case I can move it to MFS. But when you have not read the item set for any particular sized item set, then do not go in for reading it once again from the transactional database, because it is an extra expenditure there. So MFS equals MFS union frequent item set. So the count is not read here, so MFS still remains null set. And coming to this line of algorithm, that is MFCS equals MFCS minus MFS. MFS is currently null, so MFCS remains as it is. I still have two sets in MFCS. Next, calling MFS prune procedure. So I have to check whether any item set in L2 is also present in MFS. So what happens is, since my MFS is still null, MFS prune procedure is called, but since MFS is null, no action takes place there and the control comes back. Next is generate candidate C3. My K is now 2, so C3 from L2. So I have generated C3 from L2, and I called recovery. The next line is to call recovery. So since no item sets was pruned during MFS prune, recovery procedure is not called. So going to the next step in the algorithm, um, that is calling, I have not put it here, calling MFCS. After calling recovery, I have to call MFCS prune procedure. I have to call MFCS prune procedure, in which step I check whether all item sets that are present in C3 are also present in MFCS. So I see that okay, ABC is a part of this, ABD is a part of this, ACD is a part of this. So every item set in C3 is a subset of one of the item sets in MFCS. So after calling MFCS prune, there is no action taking place, and then the algorithm comes back, and where we have to increment k, so k will be equal to 3 now. Now once again I come to the initial here loop, and I see here okay, C3 is not equal to null once again. So I read the count of a C3 and MFCS. So when I read the count of sorry, when I read the count of a C3 and MFCS, I get the counts something like this. Okay, going to the next slide. Yeah, so once I get the count, I should be doing MFS equals MFS union frequent item sets in MFCS. Now if I look here, MFCS has a item set with count 2, which is now frequent. So I move that item set into MFS. So MFS, which was null, is now initialized to BCDE. So next I have to have S3 and LK. So S3 and LK, I have initialized it like this, and I'll call MFCS generation algorithm uh, if SK, that is S3, is not equal to null. So since S3 is not equal to null, I call MFCS generation algorithm, where I have S equal to ACD and MFCS equal to this, and I see that ACD is not a part of this item set here. So this one remains as it is in MFCS. Next, I see that ACD is a part of this item set here. So I have to break it. So first of all, I remove A from this set, I get BCD. So BCD is already a part of this one here, MFCS. So I don't put it because I don't put it in this set because I already have a maximal set, that is BCDE. Next I remove C, I get ABD. ABD is not a part of this, so I include it here. I remove D, ABC I get, which is not a part of this set, so I include it. So when I break down this MFCS, I get 3 sets here. So once I break it down, what do? I have the next statement, that is MFS equals MFS union frequent item sets in MFCS. So as you can see here, BCDE, whose count we have already taken, so that is 2. ABD, whose count is already taken, that is 2. In the previous slide I have 2. And ABC, whose count is already taken, that is 3. So now I hope you can make out the difference. I have some sets in MFCS here whose count is already read when I just enter the loop. I'm not doing any new reading here. So what do? MFS equals MFS union frequent item sets in MFCS. So I move all the frequent item sets in MFCS to MFS, and my MFS will have these 3 items. And what do? Since this is already all these item sets are moved to MFS, I do not need to maintain it in MFCS. So I remove all those item sets from MFCS, and that is why I have this statement MFCS equals MFCS minus MFS. So I get MFCS as null. I hope it is clear to you now why we have these two statements. The effect of these two statements may not be realized in the beginning or when we solve the problem initially. The importance of these two statements will come only when we come to the end of the algorithm, or the end of the algorithm's iteration. So mfcs will now be equal to null, and then what I have call mfs underscore prune. Now I have to check whether any of the item sets in L is a subset of any of the item sets in MFS. So if you see here, ABC is a subset here. So I can remove ABC from L3. ABD is a subset here. So I can remove ABD from L3. BCD is a subset. So I can remove BCD from MFS. BCE I can remove. So every item here, if you go on checking, is a subset of one or the other item sets in MFS. So as and when I go on removing, my L3 will become null. So since every set in L3 is subset of item sets in MFS, all items in L3 are pruned and hence L3 equal to null. I'm sorry for this slide. It, no matter how much ever times I took a image pic of this, it was coming quite dull. So what is written here is, since every set in L3 is subset of item set in MFS, all item sets in L3 are pruned and hence L3 is equal to null. So all item sets from L3 gets pruned and L3 becomes null. Next, what do? I generate a C4. My K was now 3, so I generate C4 from L3. So C4 equal to, since L3 is now null, C4 will become null. Now I have to be calling recovery procedure, since L3 has been proved. So if any item set in L3 is removed from MFS pruning, then you have to call recovery procedure. But what happens in recovery procedure is that, I'll go back to the first slide. Yeah, I have the recovery procedure here. For all item sets, L belongs to L3. Now what has happened is my L3 has become null. So even though the module is called, the control will come back because the statement will fail here, because my L3 is now set to null. So no items get recovered. Since item sets were pruned during MFS prune called recovery, but L3 is equal to null and there is no action taking place. Next, call MFCS prune procedure to prune C4. So the next step in the algorithm here, call MFCS prune procedure. So I should be checking whether every item set in L3, in C3, every item set in C4. C4 is also present in MFCS. Since my C4 is equal to null, once again there is no action taking place, and I increment K as 4. I increment K as 4 and I come back to the loop. Now since C4 is equal to null, algorithm stops there. And our final answer is MFS. The final answer will always be present in MFS. It maintains maximal frequent set, that is BCDE, ABD and ABC. I have not gone in detail with the explanation of every module of the algorithm, with an intention that the algorithm and one problem has already been covered in the class. If at all you have any doubts, you may post questions through email or you may call me up. Thank you very much.